Hello everyone, myself Sachin Gaware from RBNB College, Shrampur. In today's lecture, we continue our chapter Linear Programming Problems, in which today we see some special cases for the L.P.P. Now, for some special cases, consider the first problem. It is max z equals to 1.5x plus y subject to x plus y greater than or equals to 8 and 3x plus 5y less than or equals to 15. Now, to solve this L.P.P, first we have to plot a graph. And to plot a graph, make a table for x equals to 0, y equals to 0, and the equation of line which is obtained from the constraint. So, for the first constraint, x plus y is greater than or equals to 0, it gives x plus y equals to 8, the first line. And for the second line, it is 3x plus 5y equals to 15. 3x plus 5y equals to 15. Now, to finding the point, suppose put x equals to 0. So, we get here x equals to 0. If we put x equals to 0, we get y equals to 8. And similarly, if we put y equals to 0, we get x equals to 8. Similarly, if in second equation, if we put x equals to 0, so we get 5y equals to 15. And 5y equals to 15 gives y equals to 3. Similarly, if we put y equals to 0, we get 3x equals to 15 and 3x equals to 15 gives x equals to 5. So the next point is 5, 0. Now, we try to plot these lines on a graph. So, to draw a graph, suppose x and y axis, consider the x and y axis. Obviously, here the given constraints are x comma y is greater than or equals to 0, that is the non-negative constraints. So, we consider only the first quadrant. So, taking appropriate scale on graph, here we can write 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8 and 9. Similarly on y-axis 1, 2, 3, 4, 5, 6, 7, 8 and suppose 9. Now to plot the first line, the 0, 8 and 8, 0. Here it is the point 0, 8 and this is the 8, 0. Joining these 2 points, by joining these 2 points, we get the first line. Similarly, for the second line, the points are 0, 3 and 5, 0. So, again joining these 2 points, we get the second line. Now, after plotting these 2 lines, observe the constraints now. Now here, the first constraint is x plus y is greater than or equals to 8. Since the constraint is greater than or equals to type, we have to consider a region above the line, or we can say that a region opposite to origin side. So here we have to consider this region. Now for the second constraint, is of the type less than or equals to, and we know that whenever there is the inequality less than or equals to type, we consider a region below the line, or we can say that a region on origin sides. So this is the region. Now from this graph, we can observe that there is no common region. which satisfies both the constraint. That is, in this problem we cannot find the feasible region. Here we cannot find the feasible region. Feasible region means a region which satisfies all the given constraint, or you can say all the given condition. Such a region is absent here. So such LPP, or in such a case we say that this LPP has no feasible solution. No feasible solution, since there does not exist any feasible region. This is the first special case for the LPP. What is the first special case? Whenever we cannot find the feasible region, again, feasible region is the region which satisfies all the constraint. In such a case, we say that such a LPP has no feasible solution. This is the first case. Now, consider for the second special condition, consider the example max z equals to minus x plus 2y, subject to x plus y is greater than or equals to 5, x is greater than or equals to 3, and x plus 2y is greater than or equals to 6. Now, again, to plot this graph, we make a table which shows equation of line x equals to 0, y equals to 0. Now here it is x plus y equals to 5. Next equation is x equals to 3, and next one is x plus 2y equals to 6. These are the three equation of lines corresponds to these three constraints. Now for the first line, if we put x equals to 0, we get y equals to 5. Similarly, if we put y equals to 0 here, we get x equals to 5. Now for second line, it is the standard line passing through x equals to 3 parallel to y axis. So there is no need to find the points. Now for the third line, again if we put x equals to 0 here, we get 2y equals to 6, 2y equals to 6, which gives y equals to 3, and again if we put y equals to 0, we get x equals to 6. So the next point is 6, 0. Now again we plot a graph for these three lines. Now to plot a graph, consider the x-axis and y-axis. Again there is a one non-negative constraint is available also. So we only consider the first quadrant. We only consider the first quadrant. So taking this graph, this is the x-axis, this is y-axis, and taking the appropriate scales. So this is suppose 1, 2, 3, 4, 5, 6 and 7. Similarly here 1, 2, 3, 4, 5, 6 and 7. Now for the first line, the points are 0, 5, this point, and next point is 5, 0. This is the second point. Now joining these 2 points, we get the first line. This is the first line. Now second line is x equals to 3. This is the line x equals to 3, which is parallel to y-axis passing through the x equals to 3. This is the second line, x equals to 3. Now the third line, for the third line the first point is 0, 3 and second point is 6, 0. So connecting these 2 points, we get the third line. Now, observe the constraints. Now, first constraint is greater than or equals to type. So, we have to consider a region above the first line or opposite to origin site. So, this is the first line. Opposite to origin site of first line means this one. This is the region. Similarly, for second equation, it is greater than or equals to 0. For third, it is greater than or equals to 0. It combinedly means that we have to consider a region which is away from the origin or opposite side of origin of each of the equation or each of the line. So, this is the required feasible region. This is the required feasible region. This is the feasible region. Now, suppose the corner points are A, B and C. Now, here this feasible region is unbounded region. Feasible region is an unbounded region which takes all the points up to infinity, and the objective function is of the type maximization, and since this is the unbounded feasible region, so it includes the point infinity, at infinity. So we get the maximum value at that point. So here, in other words, we can say that we cannot find the maximum value for the given objective function. So in this case, we say that this LPP has an unbounded solution. That is, since, how to write it as? Since the feasible region is unbounded. Feasible region is unbounded and objective function, it is very important, objective function is max type or maximum type. And so, therefore, we say that the LPP has unbounded solution. The LPP has unbounded solution. This is the solution. So, remember one thing, whenever there is a objective function of a type maximization and the feasible region obtained is unbounded solution, it is very important. If both the condition will be satisfied, that is, first condition is the objective function is of the type maximization, and second condition is the feasible region is unbounded region. In that case, we say that the given LPP has an unbounded solution because it includes the point at infinity at which the objective function get the maximum value, but we cannot determine it. So we say that this LPP has an unbounded solution. Now, for the third special case, consider an example. Minimize the z equals to x plus 2y subject to x plus 2y is greater than or equals to 50, 2x plus y less than or equals to 0, 2x plus y is less than or equals to 100. Now, here, to solve this LPP, we make a table. We make a table which shows y equals to 0, x equals to 0 and the line. Now the first line is for the first constant 2x plus 2y equals to 50. For the second constant 2x minus y equals to 0, and the third is 2x plus y equals to 100. 2x plus y equals to 100. Now clearly here the line 2x plus y passes through the origin. It passes through the origin. So here we can find the 2 points by putting different values of x and y. Now for the first line, suppose put x equals to 0. When we put x equals to 0, we get 2y equals to 50. 2y equals to 50, it gives y equals to 25. Similarly, if we put y equals to 0, we get x equals to 50. So we get x equals to 50. Now for the second line, now see here, the second line is 2x minus y equals to 0, which gives y equals to 2x, which gives y equals to 2x. Now here, if we put the arbitrary values of y or x, we get the another variable. So if we put y equals to 1, we get x equals to 2. That is, this line passes through the point 2, 1. Now suppose we put y equals to suppose 4, we get x equals to 8. Suppose we put y equals to 20, we get x equals to 40. We get x equals to 40. Similarly, if we put y equals to 10, we get x equals to 20. Taking any two of these points, suppose in arbitrarily we take this line passes through the point 40, 20, and suppose second one is 20 and 10. These are the two arbitrary points. We use this method because the RHS is 0. This line passes through the origin. So now next, for the third line, if we put x equals to 0, here we get y equals to 100. We get y equals to 100. Similarly, if we put y equals to 0, we get 2x equals to 100, that is x equals to 50. That is x equals to 50. Now plotting these lines on a graph. Since there is a non-negative constant given, so we consider only the first quadrant. We consider only the first quadrant for this one. So this is the x-axis and this is y-axis. Now here the values or the points are in terms of 25, 50, 20, 40. So we take the appropriate scale, that is 1 centimeter equals to 10. So here we write here, suppose 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 and 110. Similarly here, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110 and suppose 120. Now plotting first line, first point is 0, 25. Here it is 0, 25 in between 20 and 30, and 50, 0. Here it is the point 50, 0. So joining these two points, joining these two points, this is the first line. Now for the second, it is 20, 40. Now this is the 20 here, it is 40. This is the first point, 20, 40, and next point is 20, sorry, this is the first point, 20, 10. So here it is 20, 10, and the next point is 40, 20. Suppose this is the 40 and this is the 20. So we have to draw a line passing through these points and the origin. So this is the line. This is the line which is passes through the origin. This is the second line. This is the second line. And for the third line, the point is 0, 100, this one, and 50, 0, this is the point. So again joining these 2 points, we get the third line. We get the third line. Now consider the constraints. Consider the constant. Now the first constraint is greater than or equals to type. So we have to consider a region above the first line. Second constraint is less than or equals to 0. That is the region below the line, second line. And third one is the again less than or equals to, that is the constraint below the third line. Now this is the third line. So greater than first line and below the second and third line, so this is the region. Observe here, it is greater than first line, opposite to origin site, which is below the second line and below the third line, because for second and third the constants are of the type less than or equals to, and for the first region it is greater than or equals to. Now this triangle is the feasible region. This triangle is the feasible region. Now this point, suppose it is A, this is B, and this is C. This point A is 50, 0. Now these points B and C, these points B and C are the intersection of different lines. So we find that before that, here we write, here the feasible region, here the feasible region is bounded A, B, C, A, in which, in this feasible region, we know the coordinates of point A, so in which A is 50, 0. Now we find the remaining 2 points, and for that, let's say number 1, the point B. The point B. Now observe here, this point B is the intersection of second and third line. Point B is the intersection of second and third line. So we write here, the point B is intersection of second line is 2x plus y equals to 0 and first is 2x minus y equals to 0 and second is 2x plus y equals to 100. Solving these two equations. Now to solve, take the addition. So we can write it as 2x minus y equals to 100 and 2x plus y, it is 0 and this is the 100. Now taking the addition, this plus y minus y gets cancelled. So we get 4x equals to 100, which gives x equals to 25. Putting this value x equals to 25 in any one of these two equations, we get the value of y. Suppose we put this x equals to 25 in first equation. So, since by equation, what is the equation? 2x minus y equals to 0, we can say that y equals to 2x, that is y equals to 2 into 25, that is 50. We get y equals to 50, and therefore we get the point B as 25, 50. Here the point B as 25, 50. Now, next, the point C. Now for the point C is intersection of first and second line. Now number 2, the point C is intersection of second and Point C is the intersection of first and second line. So first line is intersection of x plus 2y equals to 50, and next one is 2x minus y equals to 0. Now solving these two equations, so multiply equation second by 2 and take the addition. So we get x plus 2y equals to 50 and 4x minus 2y equals to 0. Now when we take this addition, this plus 2y minus 2y gets cancelled. So we get 5x equals to 50, and which gives x equals to 10. Now putting this value x equals to 10 in, suppose in first equation, we get, therefore by, what is the first equation? First equation is x plus 2y equals to 50. We get 10 plus 2y equals to 50, that is 2y equals to 40, that is y equals to 20. So we get the coordinates of a point C as 10, 20. Coordinates of a point C are 10, 20. We get the coordinates of this point, 10 and 20. Now consider the z. Now z equals to, now the value of z is x plus 2y. Now find this value of this z, that is the objective function, at these 3 points, corner points of a feasible region A, B and C. So z at A, that is z at the coordinates of a point A are 50, 0. So we get 50 plus 2 into 0, which is 50. Now z at B, that is z at the coordinates of B are 25, 50. So 25, 50. So we get 25 plus 2 into 50, that gives 125. And lastly z at C, that is z at 10, 20. Z at 10 and 20, we get 10 plus 2 into 20, that becomes 50. Now check, our objective function is, we have to minimize z equals to, and here the minimum value of z is 50, but it is at 2 points. The minimum value of z is at 2 points. Since here, right, mean z equals to 50 at point A and C. Since minimum value of z, or we can say that objective value of z arises at 2 points, we say that this LPP has an infinitely many solutions. This LPP has infinitely many solutions along the line segment joining these 2 points. And so here we write, therefore Z, or we can say that LPP has infinite solution along line segment AC. That is, at each point which present on line segment AC, we get the value of objective function z equals to 50, which is the minimum value. So in such a cases, that is, whenever we get the objective value, either it is minimized or maximized at more than 1 point, that is at 2 points, we say that LPP has an infinitely many solutions. This is the third and last special case for the LPP. Here we will stop. Thank you.